All right, so today we're going to take a look at 3.3, which is on a couple different things. We're going to look at what's called the factor theorem and the remainder theorem, and long division. Okay, so you might think, well, yeah, you've done long division, but we're going to do it with polynomials. Yeah, we'll talk about some of the ideas without polynomials, just regular numbers, and see what the ideas, how they kind of work out, and then we'll apply those ideas to polynomials and see what happens. So just a reminder that if something is a zero, or I call something a root, like if I have this, -1 is what I would call a root to that equation, because it's a number that I can plug in for x, and that result is 0. So -1 is called a root or a 0. Any question on that? So when you know that a number is a root, you can say something, you can say this. And this is what we call a biconditional statement. From geometry, biconditional means you can read the statement forwards and backwards, and it's true both ways. We call that the original statement and its converse. This IFF means if and only if. So if and only if is like saying this. If A, then B. If B, then A. It's a statement that's true forward and backwards. Original and converse. So let me read this statement forward, show you how it's true, and then I'll read it backwards. So the idea here is that if you have a number that's a root, then that means you can plug it into the equation and you will get 0. So if a number is a root, then you can plug it into the equation and get 0. Or you can say, if you have a number you can plug into the equation and get 0, then it is a root. So you can read it forward and you can read it backwards. Any question on the two ways I just read that? If a number is a root, you can plug it into the equation and get 0. That's the first one. If you plug a number in and get 0, then it's a root. That's the second. And they're both true. This is just a shorter way of writing everything I just said. So we're going to use long division to help us find roots of polynomials. And let's just start with an example with numbers, and then I'll explain how it applies to polynomials. So let's say I wanted you to factor something. We're not even going to factor a polynomial, just something simple, the number 12. And I tell you that 3 is a factor. How can you find the other factor of 12 knowing 3 is a factor? Yep? Can you say it again? Divided by 3, right? If I tell you that 3 is a factor, then what I'm saying is 3 times something will give you 12, right? To figure out what the something is, divide each side by 3. 12 divided by 3 is 4. And then you can check the answer. 3 times 4, yep, that gives me 12. So if you know a factor and you divide by it, it will give you the other factor. Another example, 10 is a factor, the number 10. And I'll tell you 2 is a factor. Well, okay, if you're not sure what the other factor is, take 10, divide by 2, you get 5. 5 is the other factor. 2 times 5 equals 10. Now, notice when you divide by something that's a factor, it goes in evenly. And that's very important. You get a remainder of 0. So what we're going to eventually be able to do is if we have a quick way to find remainders, we can very quickly tell, is this a factor of that? All we have to do is say, would we get a remainder of 0 if we divided it into it? If the answer is yes, it's a factor. If the answer is no, it's not a factor. Take take 11 and divide by 5. There's a remainder of 1. That means 5 is not a factor of 11. It doesn't go any that way. Okay. But the way we're going to find remainders at first, before we look at kind of the shortcut, and the shortcut only works for a specific kind of problem, we're going to look at just doing out long division. Okay, and that'll give us the remainder. So that's basically what I just said to you guys. If you divide two things and get a remainder of 0, then you know what you divided by is a factor of the numerator. So now if we start to apply that to polynomials, the reason why we might want to factor a polynomial is because it makes it easier to find the roots. If I gave you something like this, and I said, in under 2 seconds, tell me the 2 roots. Okay, done. Okay, most people probably couldn't get the answer that quick. But if you factor it, I bet most people could easily get the answer in under 2 seconds. I wrote the factored version. X plus 1, x plus 7. Now you can quickly see, oh, -1, -7. There's my 2 roots. So that's what factoring does. It makes it easy to find the roots. But not everything is always that easy to factor. So the idea here is, if this is what you had to factor, and you didn't know how to factor it, but I told you x plus 1 is a factor. What you could do is divide what you started with by what you know is a factor, and the answer that you get would be the other factor. Just like when I said, take 10, 2 is a factor, give me the other one. If you don't know how to get it, do 10 divided by 2, and you get 5. That's your answer. Exactly the same thing you can do with this. Any questions so far? Okay. So let's go through the process of long division. It's the same process you pretty much learned for numbers. You have to divide, multiply, subtract, and bring down. Okay, so we'll write the steps out first, and then we'll do an example. So the first step is if what you're dividing into, okay, your dividend. The dividend is what is under the root. The divisor is what is outside. Some people mix those up. But dividend is what's inside, divisor is what's outside. If you're missing any terms, you need to fill in a 0 for that term. Here's an example where your dividend is missing a term. It's missing the x squared term. We have to have every term represented because we're going to need columns for all of them. So for the squared terms, we would put in a plus 0x squared, just to hold the place of the x squareds. So that step is more just setting it up. We haven't even started any math yet. The next step is to take the first term of the divisor. So in this problem, it would be x, and divide it into the first term of the dividend. In this case, it would be x cubed. So we divide the first term on the outside into the first term on the inside. We write that answer down. Maybe, yeah, let's go through. I was going to say maybe we could do the step as I'm describing it, but let's describe them all first, and then we'll do the problem after. Okay, once you do that, you're going to have something written up there. You're going to take what's written up there, and you're going to distribute it out to each term in the divisor. So multiply the answer, that's technically step 2. Multiply the answer that you got from step 2 by each term on the outside, so it's a distributive property. And here's where it's very important where you write your answer. We want to make sure that we line up like terms. Okay. Okay, so we want to make sure if we have a result that's x squared, we're going to put it under the other x squareds. If we have an x, put it under the x's. So you divide, multiply, and then the next step is to subtract. You're going to have, at this point, you're going to have some things lined up in columns, and you're going to subtract them. And that pretty much completes one cycle of long division. Now you bring down the next term and do it again. So bring down the next term and repeat it. You keep repeating steps 2 through 5 until one of two things happens. Either the exponent on the inside is less than the exponent on the outside. So the exponent on the outside here is a 1. On the inside it's a 3. You've got to keep going until this exponent, that's a 3, is less than this exponent, that's a 1. Or you end up with a remainder of 0. Those are one of those two things will always happen. So you either get no remainder, or the degree of the remainder is less than the degree of the number on the outside, the degree of the divisor. And I shouldn't say it's a number on the outside. It's usually a term. Like it has a variable in it, so it's not just a number. So we'll try maybe 2 examples of this, and then look at a few other things. Okay, so let's get this one set up so that we're ready to do the process. What's the first thing I have to do here just to set it up? I'm missing something. Yep, go on.
Add in 0x squared.
Yep, so we're going to have x minus 3 on the outside, and we'll have x cubed 0x squared, bless you, bless you again, minus 8x plus 3. Okay, now we're ready to do it. So if you look at your notes, step 2 says take the first term of what's on the outside and divide it into the first term of what's on the inside. So we're going to divide x into x cubed. Hannah, if I take x cubed and divide by x, what am I left with?
Would be like x squared.
X squared. Yep. Doesn't matter where you put that. You can put that anywhere you want. Just put it above the line. But it doesn't have to be lined up with anything. Okay, if you look at your notes, the next step says to multiply that answer out to each term in the divisor. Now put the result in like columns. So Sean, what do I get if I multiply x squared times x?
X cubed.
X cubed. And Lindsay, what do I get if I multiply x squared times negative 3?
Negative 3x squared.
Yep. So now we've got some columns. And Gracie, what am I going to do? What's the next operation I do with the numbers in the columns?
What was it? I'm at a loss.
So I think this is step 4 in the steps. Did you write down the steps?
I was trying to. I only got into like the second one.
Anyone remember what's step 4? Yep.
Subtract the columns.
Subtract the columns. All right. So step 4, subtract the columns. So let's do that. And Kiana, if I subtract x cubed minus x cubed, what happens?
They cancel out.
They cancel. And what's 0x squared minus 3x squared?
Can I change those to positive so it would be like 3x squared?
Yep. So 0 plus 3x squared is what it becomes. And that's what we get when we subtract. And Leilani, what's my next step so I can do the process again?
like bring down the next term. So
Good.
start over.
Bring down the next term. Now, look at the degree of what I'm pointing to. That's a degree 2. That's a degree 1. We have to keep going until the degree here is less than the degree here. Okay? So it was a 3, now it's a 2. Let's do it again. So, take the first term on the outside and divide it into the first term on the inside. So Trevor, what's 3x squared divided by x?
3x.
3x. Multiply it back out. William, can you tell me what I get when I multiply back out?
You get 3x squared minus 9x.
Minus 9x. Okay. And how about, let's see, Jocelyn, what am I going to do with those columns?
Subtract it.
Yep. And what's 3x squared minus 3x squared?
0.
That's always going to happen. And what's negative 8x minus negative 9x?
X.
Good, x. All right, let's bring down the next term. Let's check the degree now. I have a degree 1 on the inside. I have a degree 1 on the outside. This is the last step. Because once we do it one more time, we're not going to have a variable left at this point. We're just going to end up with a number. So we had an x cubed, an x squared, an x, and then the x will be gone. Okay, so Anna, what do I get when I do my next step of dividing what's on the outside by what's on the inside?
X.
Yeah, so we're going to divide x into what? X. And what's x divided by x?
X.
If you had x squared divided by x, that would be x.
0.
We can't divide two things that aren't 0 and get 0. Yep. 1. We're dividing two things that are the same. Think of what you would have to put here, so when you distribute it back out, you get that. So it would have to be a 1. So I just kind of answered the next part. Distribute that back out. 1 times x is x. And Gemma, what else am I going to put inside?
Minus 3.
Yep. Multiply the 1 times the negative 3. And Sebastian, what am I going to do with those columns? Subtract. X minus x is gone. And Sam, what's 3 minus negative 3? 6. Okay. So, a couple different ways we can write our answer. We can write quotient is x squared plus 3x plus 1. Remainder, 6. That's one way to write it. Or you can write it kind of the way you would if you were doing this with long division in elementary school. Let's say you had 17 and you were dividing 5 into it. What's the quotient when you do 5 into 17? Yep, 3. And what's the remainder? Ava? 2. So one way you can write your answer, if you don't want to write it like that, is quotient plus remainder over divisor. And if you're like, huh? What does that mean? Well, try it. The quotient is 3. The remainder is 2. And the divisor is 5. The answer is 3 plus 2/5, or 3 and 2/5. That's what 17/5 is. 3 and 2/5. So quotient plus your remainder over the divisor. Same thing here. Quotient plus the remainder over the divisor. I have to go look it up. X minus 3. That's another way of writing the same thing. Just following the same logic that I did with numbers. Now remember, the way you can check your answer, and we're not quite at this step yet, but you can check an answer by taking the quotient times the divisor and then add the remainder. That's how you learn to check your answer when you do long division. 3 times 5 is 15, plus 2 gives you 17. Perfect. That's how you know you did it right. So keep that idea in mind. Quotient times divisor plus remainder gives you back the number you started. Okay? And we'll write that down, but that's going to come up in a little bit. And which way you write it is up to you, unless it's on the test and there's 2 separate boxes, and one says quotient and one says remainder, then you have to write it like this. If there's only one answer box on the test, then I'm looking for you to put everything in the one box. Okay, any questions on that? Let's try this one, which they've already filled in the missing terms, the squared and the linear. So let's start dividing it and see what happens. So, Jason, when I take the first term on the outside and divide it into the first term on the inside, what do I get?
X squared.
Let's see, x squared, and we'll know when we multiply it back out, but that looks pretty good to me. Let's multiply it back out. Magdalena, what do I get when I multiply x squared times all 3 of the terms in the divisor?
Okay, 2x to the 4th plus x cubed plus x squared.
Good. Plus x squared. And Skylar, what am I going to do with those columns?
Subtract them.
Yep, and subtract them. That's gone. We're going to get negative x cubed minus x cubed. That's negative 2x cubed. And 0 minus x squared. That's negative x squared. Okay, and now to start the whole process again, what am I bringing down? Yep.
The 0x.
The 0x. Now do it again. Exponent on the inside is a 3. Exponent on the outside is a 2. We have to keep going until that number is less than that number. Then you're done. All right. How about Caitlin? What do I get if I divide the first term on the outside into the first term on the inside? Let me see. So let's check. If you multiply 2x times 2x squared, do you get this first term right here? No. Sebastian?
Negative x.
All right, let's try that. So negative x times 2x squared gives me a negative, because it's negative times positive. So negative 2x cubed. Perfect. Negative x times x. Negative x times 1. Yes?
How did the negative 2 on the first part? Is there not there?
The negative 2 on the first
If you
part.
add it on next to the 0x. No,
So I see the 0x.
Yeah, minus, is that minus 2? Not
That minus 2, I haven't brought it down yet.
Oh, okay.
So that'll be one of the last things that gets brought down as the final step in the problem. All right. And now, Hannah, what do I do with these columns?
You subtract them.
What's negative 2x cubed minus negative 2x cubed?
Isn't that like 4x cubed? No, that's 0.
That's 0. What's negative x squared minus negative x squared?
0.
It's also 0. So we had two things that canceled at the same time, and whenever that happens, that's good, because that's going to eliminate one whole extra step of this cycle. Okay, we had two things that canceled. And actually, we're going to be done, because look at what's left. 0 minus x. That's a plus x. Bring down your 2. Now, look at the degree on the inside. Sean, what's the degree on what's on the inside?
My brain is just.
What's the polynomial that's on the inside right now?
Still, my brain is just like not here right now.
You help them out? Yep.
X.
Sam? X, what else is on the inside for the polynomial? X minus 2. Minus 2 is not important, really. But the polynomial is x minus 2. And what's the degree on that?
1.
That's a degree 1. What's the degree on the outside?
2.
2. 1 is smaller than 2. You're done. Can't go any further. So, answer. Quotient and remainder. And you could also write it the other way I showed you, but I'm just going to write it that way. Okay, any question on it? Looked like it might have been worse, a worse problem at first, but really things canceled out nicely, so it actually made it even shorter than the first one. Notice most of these problems, the work goes down and to the right, so you don't want to start a long division problem on the right edge of the page, because the work is going to go that way. That's one downside of this. It does take up a decent amount of space to do out a problem with long division. Okay. So let's just write something out, which is basically what I said earlier, having to do with checking your answer. Remember, to check your answer, let's just go back and look at what we did. It's, you write it down. I always have to think about it. It's your quotient times the divisor plus the remainder. And that will give you back the dividend. Your quotient times your divisor plus your remainder will always give you back the dividend. So let's write that down. This is going to be your divisor. This will be your dividend. And I can't just call them numbers because I don't know if they're numbers. They might be expressions like x cubed, things like that. But just to illustrate it with numbers, let's look at it with numbers. Let's say f of x is 19 and h of x is 3. So I'm dividing 3 into 19. Just a simple problem. I'm going to say that whenever you do a long division problem, you're always going to get a quotient and a remainder that will allow you to check your answer. In this case, your quotient would be, let's see, 3 goes into 19 6 times. And that gives you a remainder of 1. Now, I can't guarantee that the quotient and remainder are always going to be numbers. They will if you start with numbers. But if you start with something like this, the quotient and remainder might have variables in them. Depends on the problem. But I did one with numbers. So remember, we should be able to do quotient times divisor plus remainder. So quotient times divisor plus remainder. Did I write it wrong on the other page? Because this is right. I think I just switched divisor. Yeah, I did. I'm sorry. I switched those two names. 3 into 19. The number on the outside is your divisor. That is your divisor. The number on the inside is your dividend. Now it matches what I said before. divisor times your quotient plus your remainder will always give you back your dividend. That's how you check your answer. And let's check it with these numbers that I just made up. So my divisor was 3. My quotient came out to 6. My remainder came out to 1. And my dividend was 19. Is 3 times 6 plus 1, 19. Yep. So this is a formula that we know is always going to work. Dividend equals divisor times quotient plus remainder. Any questions on what's in that box? Because that's going to help us to figure out something right now. So remember that anytime you do division, the degree of the remainder is always less than the degree of the divisor, or you end up with 0. We haven't ended up with 0 yet, but the degree of the remainder is always less than the degree of the divisor. That's how you know when to stop. So let's say we had a problem of the form x minus, and fill a number in that box. And you're going to divide that into something. The degree of the remainder is always less than the degree of the divisor. What's the degree of this divisor? Ava? 1. And if the degree of the remainder is less than that, that means the degree on the remainder is a degree 0. Well, what do we call something that's degree 0? The degree 0 is just what? Yep.
0. Like it's not there.
No, it's there. There's something there, but it's simpler. It's even simpler than this. It's not even x minus a number. It's just
1.
A number. It doesn't have to be 1. The remainder could be 7 or 2. But anytime you're left with something that's degree 0, that means it's a number. It's no variable. Okay? Think of it as like x to the 0th power plus a number. All right, so if you divide by a linear polynomial, could be x minus or x plus. We're going to focus on x minus. If you divide by a linear polynomial, the remainder is just a number or a constant. And that's the very first problem I gave you guys. We divided by a linear polynomial, x minus 3. And the remainder we got was a constant. Didn't have any variables in it. So now let's rewrite this exact same formula, but let's write it for the specific case where we're dividing by x minus a number. So let me show you. Here's the two things that we're going to divide, f of x and h of x, just like I did up here. F of x and h of x. But what's on the outside, the divisor? The h of x is going to specifically be something that looks like x minus a number. Just like that. It's not going to be anything more complicated than that for this specific thing I'm showing you. So, all we're going to do in our formula is replace h of x with something specific. We're going to replace it with x minus c. Everything else stayed the same. That was h of x. H of x represents something generic. Could be anything. Now I'm saying it's not anything. It's something very specific. It's x minus some number. X minus 5, x minus 2, I don't know. But let's say we're doing a division problem where it's x minus 2. What we're getting towards here is a quick way to find the remainder without having to do the division out. Now remember, f of x is what is called, what do we call that? That's the dividend. The dividend is a formula. Right? That's the dividend. It's some formula, and you can plug any number you want into a formula. But I'm interested in plugging in something very specific. Does anybody see what I could plug in for x? Okay, what I could replace x with? And if I did that, it would only leave me with an r on the right-hand side. Caitlin? Well, if we plug in 0 for x, we would have 0 minus c, so that would give me negative c. And then I would have q of 0. And we don't know what q of 0 would be. It depends on what the quotient is. In this one, if you plug in 0 for x, you do get 0. But in this one, if you plug in 0 into the quotient formula, you get 1. So we don't know. So plugging in 0 may not necessarily leave me with just an r on the right-hand side. Magdalena?
Positive c.
Yes, positive c. If you plug positive c, in other words, if you plug in the number after the minus sign into the formula for the dividend, it will automatically give you the remainder. So if you plugged in positive c for x, just replace x with c, you would have f of c equals, replace x with c, c minus c times q of c plus r. I don't care about the quotient, because what am I going to be multiplying the quotient by? That basically wipes it out. Yeah.
0 versus c minus c.
Yeah, I need to plug the value of c into the quotient. So now you might be thinking, well, wait, so I need the quotient to find the remainder? I thought this was going to be a shortcut. It is, because when you multiply that by c minus c, you get 0. This whole part disappears. And you get the formula f of c equals r. So all you have to do to find the remainder, if you divide by something that's of the form x minus c, is plug in the number after the minus sign into f of x, and there's your remainder. Let me show you on the first one we did. What's the number after the minus sign in my divisor? Trevor?
3.
3. Take this number, plug it in for x in my dividend, and watch what happens. 3 cubed minus 8 times 3 plus 3. Sebastian, what's 3 cubed?
27.
27. 8 times 3 is 24 plus 3. What's 27 minus 24? Yep. 3 plus 3? 6. Now scroll down and look at what the remainder was that we had. 6. So if all you want to figure out is the remainder, that's all you have to do. It's a shortcut for finding the remainder. It doesn't help you to find the quotient, but it does help you find the remainder. Plug the number after the minus sign into your dividend and get the result. Let me go back to here. And that whole idea that I just explained to you is called the remainder theorem. If you want to find the remainder when you're dividing by x minus c, unfortunately it doesn't work for anything else. Okay? It has to be x minus a number in the denominator. If it's anything more complicated than that, and you want the remainder, you gotta do the whole thing out. And remember from earlier, why did I say the remainder is important? What can the remainder tell you about something? Especially if it comes out to a certain value. Anyone have a thought? Yeah?
If it's 0, then it's a factor.
Exactly. If we want to know if this is a factor of that, all you have to do is check the remainder. And now we have a quick way to do that without doing out all the long division, as long as our problem fits this pattern, which the next two problems do. So, find the remainder when f of x is divided by h of x, and then when it's divided by g of x. Okay, so two separate problems. So let's do the remainder when we divide by h of x first. So, to find the remainder, all you have to do is take what you're dividing by, look at the number after the minus sign, and fill it into the dividend, which is also called the numerator. Top. So, look at h of x. Kiana, what's the number after the minus sign there?
3.
3. And what is my dividend in this case? Or what would be my numerator?
For, that's the f of x.
Yeah, it's the f of x. It's gonna be the f of x for both. So fill 3 into f of x, and there's your answer. Whatever that comes up to. So that's going to be 27. 3 squared is 9 times 2 is 18 plus 3 minus 5. All you have to do to find the remainder without doing any long division at all. So let's see. 27 minus 18, that gives me 9. 9 plus 3 is 12. 12 minus 5 is 7. So I got a remainder of 7. Yeah.
How'd you get 18?
So I did 3 squared is 9 times 2. So what does that mean about h of x compared to f of x? Is h of x a factor? What do you think, Jason?
No.
No. It didn't go in evenly. It's like dividing 5 into 11. It doesn't go in without a remainder. So it's not a factor. All right, let's try the other one. F of x divided by g of x. And we're going to find the remainder. Question is, this time, what am I going to plug in to f of x? I said to always plug in the number after the minus sign. Well, there is no minus sign, but there kind of is a minus sign. Yep. Yep.
-1.
-1. Think of it like this. Plug in the number after the minus, after the x minus. So you are plugging in -1, and that will tell you the remainder. So we've got negative, let's see, what is that going to be? -1 cubed is -1. -1 squared is 1. 1 times 2 is 2. -1, -5. So I replaced all the x's with a -1. All right, so that's going to give me, let's see, -1 minus 2 is -3. minus 1 is negative 4, minus 5 is negative 9. So, is g of x a factor of f of x? No. Didn't go in without remainder, so it's not a factor. What is a factor? We're not really figuring that out right now. But we know these are not factors. Okay. Any question on that? So that's what we just used right there. That's called the remainder theorem. Actually, hold on one second. Let me read. So let's look at example 4. I don't think we need that part. Okay, example 4. I want to show, we're going to do it this way. Show x plus 2 is a factor of x cubed plus 5x squared plus 5x minus 2. What did we just do, or what did we just learn is a way to show that something is a factor? If, what happens? Ava?
The remainder is 0.
If you divide it into it and the remainder is 0. So let's do that. Let's divide this into this. And in fact, we don't even need to divide it, right? All we have to do is show the remainder is 0. So let's pretend that this part is f of x. This part we'll call g of x. Look at f of x and tell me what number would I plug in from f of x into g of x to get the remainder. Leilani? Negative 2. So let's find, basically doing what we just did. Find remainder of g of x divided by f of x. If it comes out to 0, then x plus 2 is a factor. Okay, so to do that, we need to find g of what Leilani just said, negative 2. Let's plug in negative 2 into g and let's hope we get 0. So negative 2 cubed is negative 8. Negative 2 squared is 4 times 5 is 20. 5 times negative 2 is negative 10 minus 2. Gracie, what's negative 8 plus 20?
12.
12. 12 minus 10 is 2. 2 minus 2 is 0. So we just showed that if you were to divide x plus 2 into g of x, you would get a remainder of 0, which proves it's a factor. Okay. So any questions on that? Right, so the book kind of refers to that as the factor theorem. I really just call it the remainder theorem in the case where it always comes out to 0, right? Because when it comes out to 0, it's a factor. If it comes out to anything other than 0, it's not a factor, right? So that's what they refer to as the factor theorem, but when you see that in the book, just use the remainder theorem like we did. So here's some equivalent statements. They all mean the same thing. So suppose that you have a number that is a solution to this equation. Like if I think I gave this example earlier. In this case, the answer is 1. Okay, so in this case, C would be 1. If you have a number that's a solution to this equation, that means that you have what's called a 0 of the function. You could also call that a root of your function. So in this case, I could say 1 is a 0 of my function. 1 is a 0, or is a root of my function. But this one is important. If you have something that is a root, then x minus it is a factor. And think about it, if I just made up something, a simple quadratic. That would factor as x plus 1, x plus 2. What is a root? What's one of the roots in that equation? Leilani?
-1.
Okay, so just think about what she just said. -1 is a root. She said -1 is a root. So x minus what she said is a factor. And is that true? Was x minus minus 1 one of the factors? Yeah. -1 is a root. X minus it has to be a factor. -2 is a root. So that means x minus -2 is a factor. And what does that mean graphically? If something is a root, that's where the graph does what? Yeah?
And then it's 0.
Think of a name of something on the graph. It has a special name.
Origin?
No, not origin. Anyone have another guess? What, if something is a root, that's where the graph does what? Yeah?
Is it where it hits the y-intercept?
No, it's not where it hits the y-axis. Because you're plugging in a value that gives you 0 for y. So you're finding an x value, like in this case, -1. And that gives me a 0 for y. So what is -1? Like if you think of it like this. -1, 0 is a point on that graph. That point is the y. Yep,
The x-intercept?
that's the x-intercept. So if you have a root, that number is the x-intercept of your graph. All right, so let's try last two questions. Here's the first one. Okay, I want you to come up with a polynomial, that's degree 3, so a cubic, that has roots of -2, 1, and 3. So you have to work backwards and figure out a polynomial. Let's start with -2. So -2 is a 0. Or you could also say -2 is a root. Let's go back and look at those equivalent statements. And what else here would help us to figure out the original polynomial? If -2 is a root. What's another way of saying that that would be helpful? So remember, you're trying to figure out a formula that would come from. And we know that if -2 is a root, something else is true. Yeah? Yep, we know -2 is a 0. What else do we know? Yeah?
Then it's an x-intercept of the graph.
Yep, we know that it crosses the x-axis there. What else do we know? Yeah?
X minus -2 is a factor.
Yes. If -2 is a root, then x minus -2, which is x plus 2, must be a factor. Because this must have come from 3 factors, and you're able to plug in each one of these numbers into one of the factors and get 0 as an answer. There's your first one. If you plug -2 in, you get 0. If 1 is a root, what does that mean? Yeah, x minus 1 is a factor. So if you plug in 1, you get 0. And what about if 3 is a root? Ava? Yeah, x minus 3 is a factor. And there, basically write it like this. There's your answer. And I could multiply that out, FOIL it out. But that's a polynomial that would cross the x-axis at exactly those 3 numbers. Okay. Any questions on that before we look at our last one? Okay. So the last one is the opposite of what you just did. I want you to find the roots. And I give you a hint to use factor by grouping. So factor by grouping means factor what you can out of the first 2 terms, and then factor what you can out of the second 2. Does anybody see what the first 2 terms have in common? Yep, Lindsay?
X squared.
X squared. Hannah, if I factor x squared out of x cubed, what am I left with?
X.
And how about if I factor it out of 2x squared?
2.
2. Now the goal is to end up with x plus 2 again. That's how factor by grouping works. Let's see what happens. What can I factor out of -4x and -8? Sam?
-4.
All right, let's try -4. What would you be left with if you factor -4 out of -4x?
X and 4.
X, and what if you factor -4 out of 8?
4.
No, because a -4 times 4 wouldn't give me -8.
So -4.
Well, I could try -4, but that still wouldn't
Oh,
give me
yeah, I
anything.
know it. It's 2.
2.
Yeah, I was confused.
-4 times 2 is -8. Now, look at that and look at that. What do both of those have in common?
X plus 2.
They both have an x plus 2. So now, you factor a second time. Pull the x plus 2 out of each one of them. If you take it out of the first one, what's left?
X squared.
X squared. And what if you take it out of the second one?
-4.
-4. Now, all we have to do is solve for the zeros, which in this case, I'll tell you they are positive and -2, if you solve each one of those. And that's it. That's factor by grouping. So that's the problem I didn't end up getting to in the first class. It doesn't take long, but we just didn't get to it. All right, and that's 3.3. So homework tonight. Is 1, 2, 4 through 6, and then 9 through 21 odd, 25, 27, and 32. So we'll go over that tomorrow. Yeah, it will be after school if anybody needs extra help tomorrow. And our test will be on Friday, 3.2 to 3.4.